This screencast is part 2 of 2 screencasts that walk us through item number 16.11 from the text. So the last screencast I left off here, where I have all of the work shown that led us to coming up with the F statistic of 6.44. Basically, this is similar to our um, T score that we would have had in a previous chapter, and we compare it to a critical T value. And how we do that is this. So in the second screen, what I have here, continued information from it. We first put together what is called an ANOVA table. The textbook has us do it by hand, but also Excel, and we'll walk through that in a little bit. Excel produces the same similar table and has a lot of information in it. And again, this all comes from the previous slide. I'm not going to go back and forth if you don't mind, but you can see that it has the sources, some text, some tables, or some research articles, if you will. If you come across a table that deals with an ANOVA, they might actually have what these sources are, meaning between where the different treatments, or in this case here, where the number of ounces of alcohol they had. So that might be what's in there in the word of between. But for now, we're keeping it very generic. So these are some of the squares that we had calculated in the previous chart. These are the degrees of freedom. If you recall, we had the degrees of freedom between, which was 4, which was 5 minus 1, because there were 5 different categories. And then degrees of freedom within. So this was the 25 minus 5. There were 25 total values or samples taken, and there were 5 different categories. So 25 minus 5 gave us the 20. And then the total, in this case here, would be the 25 minus 1. There were 25 in that capital N value and a minus 1. And then the mean standard errors here were calculated again from the previous. These were the two values that we are comparing ultimately to come up with the F score, which is the ratio between this value over this value. And it's basically saying the overall amount of variation on average between the different categories, or between these columns. And we're comparing that to the amount of variation within the individual columns. So the greater this value is, the greater this fraction is going to be when we put this number divided by or over this number. And so it's basically, again, a comparison of the variation between these groups versus within. And that's the fundamental point of these. And the greater that is, the greater we think then the amount of alcohol people drink has an effect on the amount of mistakes in the driving. So what I have here is, this is from table C in the back of the book, and this is how we compare this F statistic that we calculate compared to what's in the back of the book, basically comparing our T scores to our critical T for those T tests. So how to do that is, and basically a rule of thumb I use here, these are the degrees of freedom associated with the numerator of this ratio, and these are the degrees of freedom associated with the denominator from our ratio. And that's how we find the values. So we take a look at, and this is just a piece of that table obviously, but we go down the left column of the table to degrees of freedom of 20, which was from here, and we go across the top to the column of degrees of freedom in the numerator, which was 4, and then we find where those values meet, and our text gives us a value for an alpha of 0.05 and a value of 0.01. These are basically markings on that graph, and we're comparing where is our marking of 6.44 compared to these markings. And if it was, for example, less than 2.87, if it was less than 2.87, then we would accept the null hypothesis, and we at the level of significance of 0.05, and we'd say that there's not enough information or not enough data to show that there's a significant difference. If, for example, it was 3.22, then it would fall between these two values, and we can say, based on a level of significance or an alpha of 0.05, we can reject the null hypothesis. But if our alpha or level of significance was 0.01, then we wouldn't have a great enough F statistic to reject the null. But in this case here, we have 6.44, which is beyond 4.43, which means that even at a level of 0.01, we can reject the null hypothesis. And in the text, it asks us to approximate what our p-value is. Without Excel, we can't actually get the exact p-value, but we can get it compared to these cutoffs. So, for example, if we had an F statistic of 1.2, then that would mean that our p-value would be greater than 0.05. It would be in this, I'm kind of picturing this as like almost a thermometer here. But here we have a value of 6.44, so it's beyond the 4.43, which means we're beyond or further out on the tail, which means our p-value is less than 0.01. We can't, again, find by hand exactly what it is, but we do know that it's less than 0.01. So hopefully that helps for the first part of that problem. Now, that means that this 6.44 is allowing us to reject the null hypothesis, to say that there is somewhere in here a significant difference between these categories. The next step is to determine where. So part B asks us to find a which is called eta squared, which is the effect size in general. And how to find that, again, is the formula is in the book, but to walk us through it, and again, I'll show you in a second how we can use Excel to do this for us. This is the sum of the squares between, which is this value right here, divided by the sum of the squares of the total. So basically what it's doing is, this 911.76 is the total amount of variation, the sum of the squares of the variation there within the whole chart. And we're comparing what is the variation between these values compared to the total. So it's similar to like a percentage, but we'd like to be careful of not using percentages for this. But anyway, the calculation is that value divided by this value, which gives us 0.56. And our book tells us that that's in a window there, or a range, where we can say there's a medium effect. All right, and this again is telling us that we can reject the null hypothesis, and the categories of the amount of alcohol they have does have an effect, a medium effect, on the outcome of the number of errors driving. The next step, though, is to determine which one of these, if any, now that we know that there is a significant difference, which one of these categories is different than the other, significantly. And that's what's called the Tukey's HSD, which HSD is the honestly significant difference. And what we do here is this. First, we find this value, the HSD value. And the textbook walks us through this, but again, I want to go through it verbally if you don't mind. We first need this Q value. This Q score, or Q value here, is found in Table G in the back of the book. And what we do is we use information from the problem here where we need an alpha level. Again, I used alpha from the fact that the text compared or was using information from the example 14.14 in the book, and I went back to see that the alpha was 0.05. If I give you a problem like that, I'll spell it out a little more carefully. We need our K score, or the K value, and the K is the number of different categories. So we had 5 different columns we were comparing. And then the degrees of freedom within is also needed. Again, that's this value right here, 20. So using that table, and the textbook walks us through it also, we ended up with a Q-score of 4.23. So that's where this value came from. It came from table G with these values. Then underneath the radical sign here, underneath the square root, we need the mean squared within, which was this value right here. That goes in the numerator under the radical. And we divide by the sample size of each of these. Now, this problem, again, each of these categories had the same number of sample sizes, which was 5. All right. The next problem in the book that we had for homework, we have different sample sizes. The rule of thumb is if there are different sample sizes, then find the average sample size and make that the value here in the denominator. All right. And actually, if you think about it, the rule of thumb for all of them is if you find the average sample size. If they're all the same, then the average is that value. And if they're different, then the average will give you the value to put here. And basically what this does is this gives us the key comparison we need, and this all calculated to 8.45. What we need to do now is compare the actual differences in the means of each of those 5 different columns and find out and find the differences between these. So for example, column 1, which was 0 alcohol consumption, the average of these ended up being 3. The average in the next column was 4. The textbook gives us this, but we can also calculate it, and then I'm going to go back in a second and show you how on Excel you can find these very quickly. And we need to find, are there any pairings of these where the difference is greater than this 8.45? And I'm not going to list all of them, but what I did list was 4 of these. Just from looking at them, I know that, okay, from 3 to 4, no, that difference is not greater than 8.45. The difference is only 1. Same thing here. But then I started taking a look at the greatest difference. So the greatest difference was from 3 to 14.8. The difference of those two was 11.8, which is greater than 8.45. So yes, this is a pairing right here. We can now say there is a statistically significant difference between those two different columns or those different treatment groups. And then I continued down the line. I compared 1 to 6 and got 10.8. That also is greater than 8.45. Kept going. Compared 5.2 to 14.8. That also is greater than 8.45. I wanted to see quickly is the difference between no alcohol consumption and 4 ounces. That looked pretty close to me real quick, but I realized no. 8.2 is less than 8.45, so this one's not the case. So these 3 different comparisons, or 3 different pairs, gave us enough information to say that there is a statistically significant difference between these values. Now, to back up a little bit, this ANOVA is, again using Excel, a quick way to identify if there is a statistically significant difference somewhere within that. If this ended up being too small and we retained the null, and we found that the null hypothesis was still intact, then we wouldn't go through this process to find out what pairing has a significant difference. But because of the fact that we came up with such a high F statistic, which was greater than the values here, then we continued the process to find out, okay, which pairings in here did show a significant difference. So that's the process there by hand. Now what I want to do briefly is point out, again, how you can use Excel to do this for you as well. So if you recall, to take this information and produce this ANOVA chart, I went up to Data, and then Data Analysis, and what we're dealing in Chapter 16 here is ANOVA Single Factor. And I followed the steps in this menu to produce this chart. Now, what I'd like to walk through here is this. If you'll notice, first off, down here, it produced